Hello everyone, this is Mirzai from Cal Poly Pomona, and in this lesson we are going to talk about dual programming of an LP. For any linear programming problem, there is an associated problem called dual programming. In this lesson, we're going to focus on where that associated problem or dual problem comes from. In the following video, which is part 2, we're going to focus on how to write that dual programming given a linear programming problem. So this lesson is more focused on the concept and underlying definition for a dual programming problem. To explain dual programming, consider the linear programming problem on this screen. If I consider the first constraint of this problem and multiply the two sides of this constraint by some amount, for example, in this case, I multiply that by 6, then I have a new constraint, 3x1 plus 12x2 less than or equal to 180, which mathematically is equivalent to the initial constraint that I had. I only multiplied two sides of this constraint by a constant value. Now, if you compare the left-hand side of this constraint, the 3x1 plus 12x2, with the objective function equation, which is 3x1 plus 4x2, you notice that the coefficient of x1 in this new constraint, 3, is greater than or equal to the coefficient of x1 in the objective function. Also, you notice that 12 is greater than 4. So because the coefficient of x1 and x2 in the constraint are greater than the coefficients in the objective function, and knowing the fact that both x1 and x2 are always positive values, I can conclude that this term is always greater than or equal to my objective function. You can experiment that by plugging some values for x1 and x2. For example, you can put 4 and 5 for the value of x1 and x2. If I put 4 and 5 for the first term, I get 12, and for the second term, 60. If I add them up, it's 72. Now plug 4 and 5 here, and you see the value here that you get is 20, and here's 12, so you get 32. So basically, any value for x1 and x2 you plug in the second equation, this equation, is going to be greater than this equation. And the reason for it is that the coefficient of x1 and x2 here are greater than their equivalent in the objective function. So you can conclude that objective function is less than or equal to 180. I can write this statement as z less than or equal to 180. Now let's do the similar exercise with the second constraint of the problem. Now I'm going to take the second constraint and multiply it by 4 on both sides. So if I do that, the new constraint is going to be 12x1 plus 4x2 less than or equal to 100. Now compare the coefficient of x1 and x2 here with the coefficient of x1 and x2 in the objective function. Now what you see is that again 12 is greater than 3, and 4 is greater than or equal to 4. And as a result, this term also is greater than or equal to your objective function. So I can write this as z less than or equal to 100. Now, notice that we are trying to maximize the objective function, and now we know that the maximum of objective function cannot exceed 100. Right? So if I find the minimum value that my objective function can grow to, basically I can find a maximum value for my objective function. So now, as you see, this time we can approach the problem differently. We're trying to find to what extent we can reduce the right-hand side of this constraint, because if you find that minimum value is equivalent to the maximum of our objective function. So to achieve that, let's this time take a look at a linear combination of the first and second constraint of the problem. So this time I multiply the first constraint by 2 and add it with the second constraint. So mathematically there is no problem with doing that, and the new constraint that we get is 4x1 plus 5x2 less than or equal to 85. So to explain how this new constraint has been generated, you multiply 2 by x1 coefficient, which is 1/2, and you get 1x1, and from the second constraint you get 3x1. You add these two up and you get 4x1. Similarly, you can apply that to the second variable. 2 multiplied by 2 is 4x2 plus 1x2, you get 5x2 that provides this term. And if you multiply 2 by 30, you get 60, and you add it by 25, and you get 85. So that's how this new equation has been generated. It's a linear combination of these two constraints. Now, what you notice here again is the coefficient of x1 and x2 are greater than their equivalent in the objective function. So 4 is greater than or equal to 3, 5 is greater than or equal to 4, and then therefore this term is greater than the objective function, because any positive value of x1 and x2 that you put in this equation is going to give you a greater value than this equation. So therefore you can say z is less than or equal to 85. So if you're trying to maximize z, the value of z is not going to be anything more than 85, because mathematically it is not possible. Now, as you see, if we minimize again this value, we can achieve to the maximum of z value. So the question is, what should we put instead of 2 and 1 so that it gives us the minimum value possible on the right hand side? So let's put y1 and y2 as unknown amounts that we can multiply by these constraints so that we get the minimum value on the right hand side. So I'm going to put y1 and y2 as the multiplier because these are the value that we want to determine. So if I do that, y1 multiplied by 1/2 gives you 1/2 y1 plus 3y2. So that becomes the coefficient of x1. And then we have y1 multiplied by 2 plus y2 multiplied by 1 as the coefficient of x2. Now we want this whole term to be less than or equal to 30y1 plus 25y2, which is the linear combination of these two constraints. However, what we are trying to do is to minimize this side. We have two conditions. First, we want to make sure that the coefficient of x1 is greater than or equal to 3, and coefficient of x2 is greater than or equal to 4. So basically, we're dealing with a new optimization problem with two constraints. Let's write that down. So it's going to be 1/2 plus 3y2 should be greater than or equal to 3, which is the coefficient of objective function for x1. And the second condition is 2y1 plus y2 greater than or equal to 4, which is the second variable objective function in coefficient. Now we want to minimize the value of right-hand side here, which is 30y1 plus 25y2. So basically, we achieved to a linear programming problem. The second problem that we wrote here, we call it dual programming. We typically show W for dual programming objective function and Z for the primal or the initial programming. So that explains why any linear programming problem have a dual programming problem. In dual programming problem, we're looking at the problem from a different perspective. We start from some upper bound and try to minimize that upper bound to get to the maximum value that z can grow. The relationship between dual and primal problem are very interesting. Let's look at the dual programming properties. The very first property that we're going to review is weak duality property. If you notice, we had z less than or equal to 180, z less than or equal to 100, z less than or equal to 85, and we keep creating upper bounds for the primal problem objective function. So the weak duality property is very related to that example that we saw. We can say in a maximum LP or in a maximization LP, the value of primal objective function for any feasible solution is bounded from above by any feasible solution to its dual. So if your dual programming problem has a solution, its value is bounding the primal problem and create an upper bound for it. The same statement is true for a minimization problem. So in a minimization problem, the minimum amount is limited by a lower bound, what we call. So let's write this in a mathematical format. You can always say the value of objective function for any feasible solution in the primal problem is less than its dual objective function for any feasible solution that is given. Now, for a minimization problem, This is going to be the other way around. The value of a primal objective function for any feasible solution is bounded from below by any feasible solution to its dual. The second property is unboundedness property. If primal problem has an unbounded solution, then the dual is going to be infeasible. How? Let's explore this. This can be concluded from the first property, which is weak duality property. How? We said that in a maximization problem, we are bounded from the above by the feasible solution of its dual. Now, suppose that your primal is unbounded. It means that it can grow to infinity. Then the question would be, can you find a value for dual problem that makes this primal problem bounded? The answer is no, because this is infinity. So you cannot really find a solution and plug into your dual that restrict that value. So the unboundedness can be concluded from the weak duality property. The next property is a strong duality property, which is concluded from weak and unboundedness properties. In this property, we say that if the primal problem has a finite optimal solution, so does the dual problem. And the value of your primal and dual objective function at that optimal solution is going to be equal. So the z star is equal to w star. From there, from these three, we can conclude some relationship between dual and primal problem, which is explained in this slide. So we said if there is a feasible solution for primal, your dual is also going to be feasible. If your primal is infeasible, it means that, think about the second property we had. Either your dual is unbounded or it's infeasible. That's why your primal is infeasible. So it's either infeasible or it might be feasible and unbounded. How about if your primal is feasible and bounded? Then your dual is infeasible. It's important to know that it's a two-way relationship. So you can scratch your dual here and write it as primal, and then write this as the dual of the primal. So don't get confused that which one is primal, which one is dual. Any linear programming problem can be considered as dual or primal. Just to make it clear, if this is our primal problem and we write the dual, we get this. Now, suppose that this is your primal and I write the dual, then I get this LP. So all the relationship that we talk about primal and dual, it can be reversed. Basically, your dual can be your primal and your primal can be your dual. In the next video, we explain how you can directly write your dual programming problem given your primal without going through all those intermediate steps that we talked about in this video. If you want to learn more, please watch part 2 of a dual programming problem. Thank you.